Hi everyone. In this video, I'd like to talk about how to use sortedness in proofs. So we're going to start by reflecting sortedness with regard to our original is sorted predicate. I've got a definition of it right here on the screen. And then we'll look at some other things about sortedness that aren't really on the main line of proving sortedness correct, but I think are a good exercise both because we'll be thinking about a thing that people think about all the time, uh, property preservation, but then also it'll sort of get us warmed up for the kinds of proofs we're going to want to do about sortedness, help us understand the sorted predicate and so on. So to start with, I wanted to walk you through a proof for is sorted. So here's a definition of is sorted. Feels like a kind of concise one, feels good to me. And I want to prove that this is sorted predicate just reflects the sorted property, the inductive proposition that we defined. So let's go ahead and do it. So there's some L. We want to show that is sorted says it's true if and only if it's sorted. So I'm going to do this in separate directions. So here we have a list. We know that it's sorted, and we need to prove that it's sorted according to the inductive predicate. So to do that, we're going to use induction, right? Because this is about the whole list, and the only thing we can do induction on is L. Let's get our bits in order. Okay. Now, interestingly, the base case is straightforward. That's not the interesting part. Interestingly, the inductive case actually kind of has two parts, right? Which sorted constructor should we apply? Well, if we scroll up, it kind of depends. If L prime is nil, we can use sorted 1. Otherwise, we need sorted cons. So we need to look at L prime in a little bit more detail. Okay, so now we're in the case where L prime is empty. So we just need to prove that a singleton list is sorted. So in fact, none of this is useful at all. We don't need any of this. We just say apply sorted 1, and we're good to go. Okay, now we're in like the real inductive case. Those of you who've taken maybe some higher math classes have seen examples where people sort of choose their base cases, and they'll write, well, like, oh, I want to do a base case for n equals 0, and I want to do a base case for n equals 1, and then I'm going to do the inductive case. And what they're really doing is just this logic. In the inductive case, they're sort of doing a bunch of special cases for lower versions of arbitrary n, and then eventually they do an arbitrary one. It's perfectly valid reasoning, but the truth of the matter is what's going on here. What we were doing is sort of the real deal. Okay, so let's look at what we have to deal with. We have to prove that this pair of numbers attached to L double prime are sorted, and then we know that is sorted returns true. And then we know that, okay, if is sorted on M cons L double prime. So this isn't L double prime, just the tail of the list, it's just the partial tail, which is good, right? That's exactly what the call is being done on here, right? L refers to this whole thing. So it feels like things are kind of lining up. We need to prove sorted. We're going to want to use sorted cons. We can make a little bit of progress if we do some forward reasoning. We simple in H, okay, this is not going to be anybody's favorite, right? We get this like nested match that's like a little gross. It's possible to do this proof without seeing this nested match, but it actually makes it kind of hides some of the detail. So I'm just going to let it ride and say, well, look, for this and of these two things to be equal to true, um, they both have to be equal to true. Right, so that's going to turn that into, okay, well, that means the two parts both have to be equal to true. No big deal. And now we want to look at the two parts of sorted cons. So sorted cons has two premises, two things we need to know. First, that x is less than or equal to y. So in this context, that n is less than or equal to m. And then that sorted y cons L, that is to say sorted m cons. So we should get the sortedness bit from this one and the less than or equal to bit from this one. So each case really only needs like half of what we've got. So at this point, I'm going to apply sorted cons without doing any more to break this up, because it turns out I only need one of the two halves in either case. Okay, so what do I need to do? Well, the first thing I need to do is I need to show that n less than or equal to m. Well, I've got the gist of that right here. So let's just get that bit out. Now that, as h underscore says, well, I don't need the other thing. Like I could say h ignore, h unnecessary was what I was typing at first. So h ignore I don't need, right? This fact is irrelevant for n less than or equal to m. So writing the underscore here helps me keep a clean context, right? I think it's just an easier spot to be in. Okay, now I know LEBNM equals true. I need to show n less than or equal to m. If you have not gone back and looked at the LE exercises, I mean, by now to have gotten to this point in the file, you probably have. But if you haven't, you need to know the various lemmas that have to do with relating LEB and LE. So here, I believe this is LEB complete. And then we can apply H. Okay, great. We have discharged the first obligation of sorted cons. Let's do the second one. So now we need to show sorted M cons L double prime. Well, that's great. That's a conclusion of our IH. Assuming we can show is sorted M cons L double prime equals true. But that's actually what this is, really, right here. Right? That's going to get us that sort of automatically right here. So what we can do is this. Now we only care about the second one. We can apply RH. And now apply H works. Why is that? Well, that's why. It's the same, right? It's just simple has kind of gone too far. Now you might ask, like, well, could we just do an unfold, fold, 1-2 punch? And it turns out no, Cox still does too much unfolding here, which is really too bad. It's like not my favorite that this is what happens, but you're just kind of stuck with this partial reasoning because of the sort of like look at two elements and then recur on only having removed one element approach. But in any case, fortune favors the bold, apply H just does it for us. Okay, that is the left to right direction. If we look over here, we know we're done because it says focus next goal with dash. Okay, let's do it. This direction is much easier. Why is it easier? Well, now we have this inductive predicate sorted. That's really a hook for us, right? The real payoff of these inductive predicates is when you have them in your context, the kinds of reasoning you can do are just so much more powerful. So let's do induction on that H. Okay, this is a little bit annoying to know all the bits that we're going to have to name, but like, let's see what we need. Okay, there's the sorted nil case. Nothing to see here. The sorted cons case. Okay, we need the number name, but nobody cares after that. And then, excuse me, this is the sorted one case. And then the sorted cons case. Oh, give me n, m, and l prime. I know that n is less than or equal to m. I know that sorted ml prime, and I know an IH for m, l prime. So let's do induction. Okay, we'll have three cases. This is the sorted nil case. Easy. This is the sorted cons case. Easy. This is the, excuse me, I keep saying sorted cons. This is the sorted one case. Okay, now we're in the sorted cons case. So we need to show that is sorted n cons m cons l prime, right? This is equal to true. Okay, let's run the function a little bit. Okay, well, we need to know that LEB, NM, and match L prime, blah, blah, blah. Okay. Well, a little forward reasoning in HNM. Let's just turn that LE, that less than or equal to, into an LEB equals true. And well, that means we can now rewrite by HNM. So there's no more LE, right? Simplify away the and now we're left with this. But this is the same thing as our IH, right? You see that those are the same? So that's the whole thing. Okay, so hopefully that gives you like a bit of a tour of how to work with these things. I'm gonna do in the next video. I'll do the other properties just so none of these videos get too long. Talk to you soon.